Calvin comes bombing down the sled hill, hits the frozen pond, moving 13 meters per second. As he goes across the ice, it provides a little bit of friction, slowing him down at a rate of 4.0 meters per second squared. But there is a hole in the ice, 23 meters away. Will Calvin meet an icy doom? It's up to us to find out. All right, first thing we always do is draw a picture. We're going to be using a guess type procedure to solve this problem. Starts always with drawing a picture. All right, so let's identify a few key points. First, this event here, we'll call that our event 1. That's when Calvin hits the ice. How about over here somewhere will be where Calvin comes to rest. We'll call that event 2. His position will be x2 right there. We hope it's somewhere before the water, before the hole over here, but we can't know for sure. But as long as we put our event 2 out here, Calvin stops. We can determine by the end of this problem whether he stops before or after the water starts. For a reference point, must have a reference point, we'll choose position 1, event 1, when he hits the ice to be our reference point. So that'll be x equals 0 right there. And we know that when he hits the ice, or rather when the ice breaks apart, that is a position of 23 meters. So clearly, I'm saying that this direction is the positive x direction. Always key to decide and to draw on your picture which direction is going to be positive. That way it'll be positive. Okay, let's move on to identify our givens and our unknowns. From the information in the problem, we know that his velocity at the first event is 13 meters per second. At the second event, well, we decided that the second event is when Calvin stops. So if that's when he stops, then his velocity at that time is 0 meters per second. Now his acceleration, notice I've written negative 4.0 meters per second squared, even though it just said 4.0 meters per second squared in the problem. That's because I chose to the right to be the positive x direction. And if his velocity here is 13 and his velocity here is 0, then he slowed down from here to here. His velocity became more negative. In other words, his acceleration was in the negative direction that whole time. This is key. So acceleration is negative 4.0. And we'll identify our reference point x1 to be 0. We'll start the clock at that moment too, so we can say t1 is 0. And then we also know our delta v, v2 minus v1, the change in his velocity is negative 13 meters per second. That's a lot of information we know from just 3 numbers in the problem. Actually, we didn't even use this number over here, 23. That's just something we're going to compare our answer to later on. All right, our unknowns of the 10 variables that appear in our constant acceleration equation. We don't know x2. We don't know where he comes to a stop. We don't know when he comes to a stop. And so then we don't know the change in position from here to here. We don't know the change in time from here to here. Those are our unknowns. What we would like to know is especially this position. We want to know if this occurs before or after the ice breaks apart. All right, our next step is to choose an equation to use. To do so, look back at your constant acceleration equations, look through, and decide which ones are solvable. Let's take them one at a time. Delta v, do we know delta v? Yes, it's one of our givens. I'll put a little check by it. Do we know the acceleration? Yes, it's a given. Do we know delta t? No. Okay, so in this equation, I have one unknown. Therefore, I could solve this equation for the change in time between events 1 and 2. But let's keep going. Let's look at this next equation. Do I know delta x? No, it's unknown. Do I know the initial velocity? Yes, I do. Do I know the change in time? No. Do I know the acceleration? Yes. Do I know the change in time? No. All right, looking at this equation, I have 2 unknowns in this equation. Therefore, I can't solve it. If there's more than one unknown, not solvable. Can't use this one. Let's look at the next one. Change in the velocity? Yes, I know the change in the velocity. Well, notice this is change in v squared. This is change in v. But if I know both v's, then I know the change in v squared as well. Do I know the acceleration? Yes, I do. Do I know delta x? No, I don't. Aha, but this equation now has one unknown, so I can solve it also. I could solve this one, or I could solve this one. Which one are we going to pick? Well, what do we want to know most? Do we care how long it takes him to slow down? Not really. We just care where he stops. So we would like to know delta x. We would like to solve this equation right here. So we'll pick this one. There's our equation, written it out in its generic form. Then underneath it, I've substituted in our specific variables. And in our case, v2 is 0. That's when he comes to rest. So I can drop that variable from the equation right away. It's going to go away. Now we need to solve this algebraically for delta x. That's what we want to solve for. To get it by itself, I'm going to divide both sides by 2a. That 2a cancels that 2a, and I can rewrite this moving delta x to the other side as delta x equals negative v1 squared, or the opposite of v1 squared, as I like to say, over 2a. There we go. There's our algebraic solution to this situation. The last step is substituting in our numerical values. Okay, everything on this side of the equation is one of our givens, so we can just substitute these numbers in. 13 in for v1 and negative 4 for a. Plug them in, do the arithmetic, comes out to be 21 meters. Did Calvin survive? Now we know that x2 is 21 meters from x1. Aha, 21 meters, that's less than 23 meters. Therefore, he came to a stop a couple meters shy of certain death.